Welcome. I have some questions from College Board. Question 8. They tell us the figure above shows the graph of a function, and here, function f, with domain from 0 to 4. Which of the following statements are true? Limits of the function when x approaches 2 from left side. Limit of the function when x approaches 2 from right side exists. And limits of the function when x approaches 2 in general from left and right together. So what we could do here is to draw a vertical line, imaginary vertical line, cross. Okay, let's make it solid here. Lock it in. Okay, and then we take, draw a vertical line, cross x equals 2 in here, and investigate the limits to the left and to the right. You see, the limits to the left, it's, let's say it's, this is a 1, 2, 3, yeah, let's fix it here. Okay, it's 1, 2, 3. Okay. So the limits from left, as you see, it's when x approaches 2, you see that y is 3. So the limits of the function when x approaches 2 from left side is 3. And then from right side of this vertical line, you see that when x approaches 2 from right side, y will be 2. The function will be 2. So the limits of f of x, yes, when x approaches 2 from right side, it will be 2. So the limits from left side exist, yes, the limit from left side exists and from right side exists. But when you look at the limits in general, if you see that left side doesn't equal right side, that means it doesn't exist at 2 in general. At 2 from left, yes, at 2 from right, yes, but we have two different limits. So only first and second, the answer would be C. I have another question here, which is the derivative of the function f given by f dash of x equals x squared cosine x squared. I grabbed this question from the section, the allow the calculator, which is f dash of x equals x squared cosine x squared. How many points of inflection does the graph of function f between the interval -2 to 2? How many inflection points? How many inflection points means you deal with the second derivative. So yes, we could find the second derivative and equal it to 0 and then solve it for x. That's algebraically. We'll do it. Graphically, you graph this function. Just I want to give you a hint. If it's in the section that they don't allow they don't allow graphing calculator, you have to do it algebraically. But if it's in the section and it's already in the section that they allow the calculator, you graph the derivative of the function. And then here I have it in this mass and I have it in Texas Instruments 84 plus, and also in this mass here. Let's graph x squared cosine x squared, and it's in here. X squared cosine x squared, this is the function. Let me make a copy of that snapshot to investigate the function. Yeah, here. Okay. So let's copy. We'll go to our presentation. Separate slide, separated slide, special one. Yeah. Wow. Let's make it smaller. Let's make it smaller and smaller. Better now. Yeah. So this is the function that we graph, which is x squared cosine x squared. That's the derivative of the function. So if you want to find the second derivative, that means you look for the tangent line equals 0. Tangent line slope equals 0. So tangent line, you could imagine how many lines we could have it here. Has a slope. How many tangent line has a slope equals 0? So let's do that here. Make it in blue. Okay. Yeah, blue line. Enough. Okay. So you see this point? 1 and here. So this will be inflection point. When you graph the second derivative, it will be inflection point. And let me lock this here. Lock it. Yes. So this is the first, which is the second derivative equals 0 in here. And also in here, at this point, the second derivative. So we have 2 points. And also at 0. That's all between -2 and 2. By the way, we could have infinity of inflection points if you have complicated function like this. But we're looking between -2 and 2. Between -2 and 2, we have 3 positions for inflection point. This is position 1 here, this one, and this is position 2, and this is position 3. If you draw tangent line, the tangent line, it will touch the function in this point, and it will have a slope of 0. And this one, the same here at this point and at this point. So the answer for this is 3 inflection points, 3 inflections points. If you want to do it algebraically, of course, you're going to do the second derivative, which is you deal with product rules. Derivative of first, which is 2x. Let's do it in here. Okay. Derivative of first, 2x times cosine x squared. Plus, you keep x squared, but you need to do the derivative of second. Derivative of second. Derivative of cosine is negative sine x squared. And derivative of inside x squared, which is 2x. Let's simplify it here. 2x cosine x squared, and negative times 2x to the second x would be negative 2x to the third times sine x squared. Okay. Equal it to 0 to find the inflection point. So this is the second derivative. Then you equal it to 0. You could take from the 2 quantities here, you could take 2x is common here, 2x out, common. 2x is common. Divide each term by 2x, then cosine x squared left. And here is negative x sine x squared. So now we have like 2 quantities multiplied equals 0. 2x and cosine square, minus x sine x squared. We must have at least one of them equals 0 to have result equals 0. So first one, 2x equal to 0. If you equal 2x to 0, of course x equals 0. So this is one of the solutions. And the second part, which is x cosine x squared minus x sine x squared equal to 0. When you equal it to 0, you add x sine x squared to both sides. So x cosine x squared equals positive x sine x squared. Then we could find that we could solve the equation. Divide by sine. So cosine over sine equals x. Then cosine over sine is cotangent. Cotangent x squared equals x. Then when you project cotangent x squared equals x, we have two possibilities for cotangent x. Cotangent. What's tangent of 45? I heard you, it's 1. And also cotangent of 45 is 1. So we have, on this case, we have two solutions, cotangent of 45 and negative 45. We have two solutions in here and in here, equals 1. So we have two inflections point plus the third, which is 0 and 0. We have three inflection points in general. So the answer of this question is 3 points, 3 inflection points. There's a question here. The answer is 3 inflection points. Okay, graphically and algebraically. If you have comment in YouTube videos, and I will respond as soon as possible. Now we have question 10. F of x equals ln of x plus 4 plus e to the negative 3x. So this is the function. F of x equals natural log ln of x plus 4 plus e to the negative 3x. And we want to find the derivative, evaluate the derivative at 0. So let's find the derivative first. Derivative of ln is 1 over. Derivative of ln of x is 1 over x. Derivative of ln of anything is 1 divided by that thing. So it will be 1 over whatever it has, x plus 4 plus e to the negative 3x. Good. Times, we use chain rule, derivative of inside. Derivative of x is 1. Derivative of 4 is 0, don't count it. Derivative of e to the negative 3x, still e to the negative 3x, times derivative of negative 3x, which is negative 3, so minus 3. That's the derivative of the function. We want to evaluate the derivative when x is 0. So we'll substitute for 0. So it's 1 over 0 plus 4, 0 plus 4, and this is e to the 0, negative 5 times, negative 3 times 0 is 0, still 0, times 1 minus 3 e, and this is negative 3 times 0 is still 0. We're about to finish. So here will be 1 over e to the 0 is 1. 1 times 4 is 4. So it will be 1/4. And this will be 1 minus e to the 0 is 1 times 3 is 3. Then it's 1 minus 3 is -2. Then that's we still have derivative of x is 1. We left 1 here. Sorry. We have 1 here. It will be 5. Yeah, I know that you capture it. I know that you capture it. We have 1 over here. Derivative of x is 1. So 1 plus 4 is 5. So numerator will be -2. Divide by denominator, which is 5. Finally will be -2/5.